Welcome back to the classroom. My name is Mr. Wong. Today we're going to be covering Module 3, Waves and Thermodynamics. Inquiry question 5, which is on thermodynamics, and this is the dot point we're going to look into. We're more specifically focusing on thermoconductivity, so let's define what it is and also how can we calculate for it. So, last video that we made, we talked about how heat by conduction works. The concept of conduction is where heat is transferred between particles through elastic collisions, by assumption, elastic collisions between the particles inside an object. It will transfer from a high temperature location to a low temperature location. When a particle has a high temperature, it means also they have a high kinetic energy, so they are going to vibrate really violently compared to the low temperatures. When they vibrate, they're going to collide with another particle, and that transfers some of that energy over. In that process, we can talk about how easily it is to transfer heat from one side to another through a concept called thermoconductivity. So thermoconductivity, as you can see, using some of the materials we have, silver has a really high thermoconductivity, copper as well, aluminium as well, cast iron not as well, but still better than a brick, ice and water. You can see these are all metals, and then water and ice are obviously non-metals. So that's where we lie in terms of differentiating between conductors and insulators as well. You can think of heat conduction similar to this animation here. You can see particles, once they interact with other vibrating particles, they also start to vibrate a lot more violently. So how can we measure thermoconductivity? Thermoconductivity, which is a K constant value, so each material will have its own specific ability to conduct heat, is an expression of how easily heat is transferred through that particular object. So we're looking at the distance between where the heat is being transferred. We're looking at the surface area or the cross-sectional area of the material. We're also looking at the temperature change, and we're also looking at the quantity of heat transferred. So all these factors, area, thermoconductivity, change in temperature, and the length of the material will affect how much heat can transfer within a specific time period, so to say. Okay, so the factors that can influence how fast heat is transferred: thermoconductivity constant, the material's cross-sectional area, the length or the thickness of the material, and then the temperature difference. The formula can be expressed like so. So capital Q represents the heat or the quantity of heat. So I might just put that down in case someone wonders what it is. So capital Q is the heat. Lowercase t represents time, that's measured in seconds. Capital T represents the change in temperature. So don't confuse capital T and lowercase t. D is the length of the material or the thickness. K is your constant. In any kind of question related to thermoconductivity, they will give you a value, so don't worry. And then we have one capital A, which is the surface area perpendicular to the direction of heat flow. So these are all the units you use, but it shouldn't be much of an issue because they do give you these units in a question. So this is thermoconductivity for you. Let's have a look at this question here. A really big multiple choice, but we'll go through it. A person wants to replace the window on her house, but she doesn't want her heating and cooling bills to change. The original window on the wall of the house has an area A and thickness D, and it is made from glass that has a thermal conductivity constant of K. Okay, so if you recall, our equation, change in T, we have A, and then we have D, and then K constant. Which of the following changes could be made to the window that would leave the rate of thermoconduction the same as the original window? Would it be double the area, double the thickness, quadruple the K constant? Would it be B? Would it be C? Would it be D? I'll give you 3 seconds and then I'll reveal the answer. So in this case, the answer is B. Try and substitute that into your equation and see if that explains why the thermoconduction rate is the same. Okay, so let's have a look at this question. The end of a 30 centimeter long copper rod at 20 degrees Celsius is dropped into a campfire of 400 degrees Celsius. If the rod has a diameter of 1 centimeter, what rate will the heat be transferred along the length of the rod? So let's firstly work out what the radius is, because we are imagining we have a rod and heat is going through perpendicularly of the rod. That would be 0.5 centimeters, because the radius is half the sort of cross-sectional length of a circle. So the area in this case is pi 0.5 10 to the minus 2 squared. We know what our K constant is. That's given to us there. We know the distance, 30 centimeters. We'll convert that into meters. We know what our temperature change is, because that's just 400 subtracted by 20, so that's 380. Okay, so that should be enough information for us to answer this question. So let's do our substitution. And then we have 2 or pi 0.5. And then we have our change in temperature. And we also have the distance. Okay, let's plug it into the calculator. This gives me an answer. If I round it off, let's see, the lowest sig figs I use is 1, but we'll round it off to 3 sig figs just to make it look a bit nicer in this case. 39.6 joules, because we have energy up here. The SI units for time is seconds, so joules per a second. That's how you do this question here. Alright, we have question 6, question 7. So the thermal conductivity of aluminium is this value here. How much energy is transferred through a distance of 40 centimeters in a block of aluminium, with one side at 60 degrees Celsius, the other at 40 degrees Celsius in 300 seconds. So how much energy is transferred, and then this one is calculate the rate of energy transfer. Okay, so in this case, Q is the subject of our equation. We need to have K, we need to have A, we need to have change in temperature, we need distance, and we also have time to consider. So 204, we have a distance of 40 centimeters is our distance. The area is given to you, so it's 0.25. The change in temperature we have here is 50 degrees times by 300 seconds. Alright, let's put that in the calculator as well. So that gives us an answer of 1912500 joules of energy. You can convert it into kilojoules as well if you want, or even potentially megajoules, but let's just leave it as this number here. The next one we want to calculate is the rate of energy transfer, so QT is what we're looking for. I know what K is, that's already given to me, so 0.15. We have the area, which is 1. We have the temperature change, which is 11. We have the overall distance or thickness, so 10 to the power of 2 minus 2. There we go. That gives us 16.5 joules per second of energy transfer. Okay, so that's how you do the question. Alright, so that concludes our lesson for today. We've covered through thermoconductivity. We've looked at specific metals will have a different type of thermoconductivity, and that's what affects how fast heat is transferred between different materials. Hopefully this section has been useful to you in understanding more about thermodynamics. If you do like watching things about thermodynamics, there are more playlists that you can look into, but you know, if you've had enough for the day and want to take a break, that's all good as well. Give it a like, appreciate all the positivity, and have a great day.